Okay, kia ora everyone. Welcome to Level 3 Physics 2020. It's going to be all for the paper. I know a lot of you have mock exams coming up right now, so we're going to start grinding through a few more of these. I might do some calculus and chemistry as well. Okay, let's get into it. Question 1's about a plane. So Tom's a pilot, he's flying a plane. He's going to give us the mass of the plane, and he can fly it straight, so like this, or he can fly it in a circular path, so the plane's banked at an angle. So if you think about that, it's going to sort of go around and come back. A bit like a car on a track with a banked angle. Think of like a racetrack or something. So they want us to draw a force diagram for these two scenarios. So the first scenario, the net force on the plane is 0. It's feeling a gravity force downwards, and it's feeling an equal and opposite lift force upwards. Perhaps we should put this in a different colour. In the second scenario, the gravity will still act downwards. However, the lift force or the reaction force is always at right angles to the sort of to the plane, as it were. And it's always like this. And if you think this is now unbalanced, and the reason it's unbalanced, and we'll get into this really in the next questions, is that there is this component in this way, which is actually the centripetal force. That's the bit which is making it go in a circle. From a top-down view, it would look a bit like this. This plane's going around in a circle, it's got this centripetal bit going in this. That's not necessary, but it's just probably important for the next question. Compare the size of the force due to gravity and lift force in the plane when Tom flies at a horizontal straight line and when he flies at the horizontal circle. When he flies it at a straight line, I can't spell great. Straight line, the gravity and lift force balance each other. And you could say net force 0. At an angle, the vertical component of the lift force matches gravity, while which implies the entire lift vector is greater than gravity. And you can draw a little diagram to show why that is. Doesn't make any sense. Beforehand it looked like this is Fg and Fl, but now it's the same Fg vector, but now the vertical bit of Fl has to be the same because its plane's not moving up and down, so the vertical forces have to be balanced. However, it's going out this side. When you think about Pythagoras' theorem, like this hypotenuse will definitely be bigger. A has to be bigger than B. So it has to be bigger than the gravity force. Okay. On one occasion, Tom flies a plane with this mass, with the speed of this speed at 35 degrees to the horizontal. How do they raise the circle? Diagram really is going to assist here. Consider our forces involved. We've got our gravity force. We've got our lift force. This is the centripetal force inwards, and this guy here has the same size as Fg. These two dots are the components of the lift force. So what we can say here is that, this is an angle. Now, you did a bit of trigonometric skills here, but what you can say, maybe it would be better for the components of this, but what you can say is that the tangent of that angle there will be the opposite side, which is the same length as this guy here, right? the centripetal force divided by the adjacent side, which is the same size as Fg. So this equation has to hold true. Therefore, the centripetal force is equal to gravity force, mg, times tan theta. Now, the fact that we're in a plane implies we're quite far above the surface of Earth, so using mg probably isn't the best approximation, because g changes with height. The gravitational field strength as 9.81, that's on the surface of Earth. When you move further away from Earth, that changes. Gravity gets weaker. Think of Newton's gravity equation having that 1 on r squared term. As you make that quite big, the force goes down. But this equation here that we've just derived is very useful because it allows us to say mv squared on r equals mg tan theta. And so v squared on r equals g tan theta. That's quite profound, realizing that the mass actually cancels out. That's quite an important concept. And then some algebra rearrangement yields that v squared on g tan theta is the radius, and plugging in our numbers, 54 squared divided by 9.81 times the tangent of 35, make sure you're in degrees, should yield you about 425 meters per second, which sounds about right for a plane. Not meters per second, meters. Sounds about right. It's quite a big circle. Tom then flies his plane at a height above the surface of Earth, counting the gravitational field strength. So we're trying to find the local G. G is 9.81 at the surface of Earth. What is it this far above the surface of Earth? That's what the question's saying. So recall that Newton's gravity force is given by this expression here. R is the radius of Earth, x is the distance above the surface of Earth. So think of this as R, and this is x. So that's the total distance away from the centre of Earth. So that's the effective sort of radius, as it were. And that gravity force must be equal to m times g. I'm going to call it g1. This is the local gravitational field strength at this height. Again, the masses cancel, and we're left with g1 equals big G, mass of Earth, divided by r plus x squared. Subbing our numbers, 6.67 times 10 to the minus 11 times the mass of Earth, which is 5.98 times 10 to the 24, divided by the radius of Earth, which is 6.37 times 10 to the 6, plus 1.28 times 10 to the 4 on the bottom. Square that, and you should get 9.79 newtons per kilogram. Newtons per kilogram is quite a good unit, describes the amount of force per weight, per mass, not per weight, per mass. You can also use meters per second if they are equivalent. And notice this is not that much smaller than 9.81, which should make sense, right? We're only, what is that one? 2.8 times 10 to the 4. We're only about 13 kilometers off the surface of Earth. So it's not actually a big effect. It's still relatively similar. Anyway, Sandra dives from a diving board that's 10 meters high. She finds she can do somersault by tucking her body in. Okay, yada yada yada. There's the information. Rotational inertia question, essentially. Show that our angular momentum is this. Well, our angular momentum will be given by rotational inertia times angular velocity. They give us the angular velocity. We don't have the rotational inertia. They do tell us that is 2/5 mr squared, which we can calculate because we've been given the mass and given the radius of the model sphere. So 2/5 times the 60 kilograms times the 0.2 squared should give you 0.96 kg meters squared is the unit there. And then subbing that in over here, we get 0.96 times 9.56 radians per second. We get 9.2 kg meters squared per second. That is the angular momentum. Awesome. 9.2, 9.18. Yeah, alright, yeah, 9.18. If you put it in, that's what they want it to. She owns her body there by changing rotational inertia. Explain what effects will have on her rotational motion. Okay, by straightening out, she increases her rotational inertia because more of her mass is further from the rotational axis. So, like, recall I equals mr squared, or I is proportional to mr squared. Yeah, so she gets, everything's further away from rotational axis, I is proportional to mr squared, she gets a higher rotational inertia. Therefore, since no external torque is present, nothing is pushing on her essentially, what's causing her to rotate, her angular velocity decreases since her angular velocity decreases since L is constant. So angular momentum is constant. So if inertia goes up, then angular velocity has to go down. Rotational kinetic energy is given by half I omega squared, which is the same as saying half times the angular momentum omega. Think of changing out, I should put another line in there. Same as saying half IWW, which is the same as saying half LW. You can consider this bit to just be the angular momentum. Therefore, the rotational kinetic energy goes down since omega goes down. So if this omega goes down, then rotational kinetic energy goes down, because half L never changes. That's the idea there. Takes 100.28 seconds, measurement becomes this. Alright. The old angular momentum was 9.18. So 9.18 has to be equal to the rotational inertia now times the new angular velocity. This is conservation of angular momentum. So the final angular velocity must be 9.18 divided by 4.8, which is about 1.9 radians per second. So the angular deceleration is equal to 1.9 radians per second. So that's the final minus the initial, which was 9.56. If you recall from up here, 9.56 divided by the time it took. Remember, that's the change in omega divided by the change in time. And if we do that calculation, we get about negative 27.4 radians per second per second. Tapu does 2 complete somersaults in 1.25 seconds. So recall 2 revolutions equals 4 pi radians. Therefore, omega is equal to the change in beta divided by the change in time. While he's revolved 4 pi radians divided by 1.25 seconds. That should give us about 10 radians per second. 306 in a rigid swing that is 3 meters long, should have the period of the same swing is 3.5 seconds. Look at the formula sheet, time period is given by this equation here. Summing in our numbers, 2 pi square root of 3 divided by g, which is 9.81, and we get 3.47, which is 3.5 seconds, so 1 significant figure, or 1 decimal point. Explain, giving reasons, how the period of swing where effective swing stands up. Consider the swing beforehand. Serena's sitting down, whose center of mass is about here. This is the length of the swing initially. Consider the swing after she stands up. Well, the swing's still the same length. However, her center of mass is probably more so about here. You can see looking at the diagram, it's probably about there. And so really the effective length of the system is less. So your argument here should be the effective length decreases, so T decreases. because the time period is proportional to the square root of length, if you look at the equation. If L goes down, then T will go down. The graph below is at a restoring force against Y, which is the horizontal displacement. Explain how this shows that the swing is not a simple harmonic motion. Well, it's linear, so F is some constant times X. Linear, so forces, well, not X, Y. So force is proportional to Y. And then notice that the gradient is less than 0, implies that F is greater than 0 when Y is less than 0, which you can verify here, like F is greater than 0, Y is less than 0, and F is less than 0 when Y is greater than 0. So F is less than 0, Y is greater than 0. This implies that they're opposite in direction, which should make intuitive sense because when you're on a swing, right, if you go out this way and you define this to be positive, then the force will be back this way, which is negative. Similarly, if you go out this way and you define this to be negative, the force will be back this way, which is positive. Your force is always going to go against where you are. If you swing out this way, the force will try to pull you back this way. If you swing out this way, the force will try to pull you back this way. I don't use reference circles, so whoops. If you look at the formula sheet, you should get the following equation out of it. Cosine omega t. This describes the equilibrium displacement. So this looks like W is 2 pi divided by the time period, so 2 pi divided by 3.5 comes out to be about 1.8 or 1.795. So this describes if she starts at A and starts to swing towards B and then back, this describes how far away she is. So it oscillates between 1.5 and minus 1.5, which should make logical sense because she never gets further away than 1.5 meters from the middle. This would be a position of 0. If we define this to be positive 1.5, so she's starting at positive 1.5, we ask the question, what is T when she is 0.5 meters from B? So she's here. So when Y is negative 1. So this is a Y value of negative 1 going this way. This is a Y value of positive 1.5 over here. So this implies 0.5 meters is left here. You can solve this. Negative 1 on 1.5 equals cosine 1.795t. And therefore, if you make sure you're in radians, if you take arc cos of that, negative 1 on 1.5 will give you 2.3 radians equals 1.795t. So the time it takes to get there is 2.3 on 1.795, which is about 1.28 seconds. And then you look at the formula sheet again and you'll find velocity is equal to A omega sine omega t with a negative sign. This comes from differentiation. If you know differentiation, you'll see immediately why that is. And then you ask, what is the velocity at 1.28 seconds? Well, that's just negative 1.5 times the angular frequency times the sine of 1.795 times that time, which is 1.28. And if you chuck all of that into your calculator, negative 1.5 times 1.795 times sine 1.795 times 1.28, you should be throwing out an answer about negative 2 meters per second. Negative 2 just accounts for direction. It means it's going 2 meters per second to the right. This method I find better than the reference circle. It's got a bit more logic to it. And that's it. It's 20 minutes. I've sped through this because I have to go to work, unfortunately. I've got a class in 5 minutes to teach. If you're interested in online tutoring, by the way, just leave a comment. uh, yeah, I am legally employed, so sure. Um, but that's it. I'm just supposed to do these for free. These are fun. I hope you get something out of them. Cool. We'll leave it there. See you next time.